Math 2414, Taylor and Maclaurin series, video 1, creating a series for a general function. In the previous series of videos, we discussed making power series for a variety of functions, but every function that we made a series for was based on the form of the sum of a geometric series. In other words, every time we did a problem that said find the power series for a function, it had something to do with an expression of that form, a over 1 minus r, and then we used the fact that that was equal to the sum of a geometric series, whose first term was the numerator, and whose ratio was the number being subtracted from 1. And we also had the condition that the absolute value of the ratio had to be less than 1. But that was assuming that the function or its derivative or its antiderivative could look like this. If the function's derivative looked like that, then we found the series for the derivative and then found the antiderivative to get the series of the original function. Or if the function's antiderivative looked like this, then we found the series for the antiderivative and then took the derivative of that to get the series for the original function. But what if none of f of x, its derivative, or its antiderivative had the same form as the sum of a geometric series? In other words, what if we can't do what we did before? For example, consider the function e to the x. Clearly, that does not look like this, nor does its derivative or antiderivative, both of which are e to the x, plus c if you do the antiderivative. So it kind of raises a question, how do we get a power series for a function when we can't just take advantage of a geometric series? Well, we're going to figure that out, and then the result's going to be very nice. So before we do this, we're going to make some assumptions about the function that we're using. We're going to make two assumptions about it, actually. We're going to assume that a function f of x has two properties. Number one, our function can be differentiated as many times as we desire. In other words, we can take its derivative repeatedly. Now, if it's a polynomial, then eventually its derivative would equal 0. But there are other functions that are infinitely differentiable without becoming 0, namely trig functions, e to the x, natural log, square roots, etc., etc. Polynomial will always become 0 when you differentiate it enough. This is called infinitely differentiable. The second thing we're going to assume about our function is that it can be represented as a series centered around some value x equals a, and that series converges to f of x on some interval centered at x equals a with some radius r. In other words, the series converges on some interval of the form a minus r, a plus r for some positive value of r. So basically, we're assuming that our function can look like this, and we get convergence somewhere. Remember, we always get convergence at the center, because when you put in whatever the center equals, in this case, if you put in x equals a here, here, and here, everything disappears except for the first guy. Technically, if you were to write out what the series said to do for n equals 0, it would be c0 times x minus a to the 0. But we're assuming that this is always equal to 1, even under the case of 0 to the 0, which is technically indeterminate, but for the purposes of where we're going to assume that's equal to 1. And hence, we can always write the first part of the series just as the first coefficient, c0. All right, so if we assume that we can take the derivative as many times as we want, and that we can write the function of this form, in order to find the series, it boils down to finding the coefficients. What number goes here? What number goes here? And here and here. Remember, we'll be given the center of x equals a. It'll be a number. But what about the coefficients? So that's really what this boils down to. How do we find the coefficients for a power series representation of a general function? Well, let's take a look at it. Here I have a general representation of a power series, assuming convergence on some interval centered at A. And let's see what we can do to figure out the coefficients. Now we're going to figure them out one at a time. Now we know a function series will always converge at its center. So the first thing we're going to do is we're going to let x equal A and see what happens. We get f of A on the left, C0 plus C1, remember x is equal to A minus A, plus C2, A minus A squared. And I think you can tell what's going to happen with most of these terms. Most of these terms are going to disappear because the center will make x minus A equal to 0. So that's gone, that's gone, that's gone, and that's gone. So the only thing that's left is C0, and we instantly get that the constant term of our infinitely long polynomial is just the original function evaluated at its center. In other words, the first coefficient is just f of A. Well, that wasn't too bad, but what about the other coefficients? Should we put in something different to find them? Well, let's get rid of all the stuff in pink, and then I'm going to write on the top what we just figured out, that the first coefficient, the 0th, if you will, is just the function evaluated at its center. But can we choose a different value to put in for x and calculate C1? And the answer is no, at least not yet. Because if we put in anything besides the center in for the x, then none of these parentheses will disappear, and we'll have an expression with an infinite number of coefficients. So we're not as lucky when we plugged in the center to find the first coefficient, or rather I should say the 0th coefficient, because in that case we can make everything disappear except the first guy. But putting in something besides A won't give us the luxury of canceling everything except one piece. So how can we possibly figure out the remaining coefficients? It doesn't seem like we can kill off all the polynomial, all the series, like we did when we found the first one. Well, remember, we're assuming two things about this function. Number one, that it can be written as a series, and number two, that it's infinitely differentiable, meaning that we can take as many derivatives as we want. So why don't we take a derivative and see what happens? So for our second move, we're going to find the derivative. Actually, let's go ahead and find the derivative and see why that's a good idea. Now, if you're worried about taking the derivative of this thing, don't worry, it's just a polynomial. We use the power rule repeatedly. And I've got the hiccups, excuse me. I'm going to pause the video while I get rid of these hiccups. I believe the hiccups are gone. So we were taking the derivative of this function, which looks a little intimidating, but it's just a polynomial. Granted, it's not just x to powers. It's x minus A to powers, which would invoke the chain rule. But the derivative of each parentheses is just 1, so the chain rule really won't do anything here. Let's take the derivative of this guy. The derivative of the first term is just 0, so it's gone. For the derivative of the second term, we would leave the coefficient alone and then times the derivative of x minus A, but that would just be the first coefficient times 1. So the derivative of C1 times x minus A is just C1. And now let's take the derivative of the second term by using the power rule. Bring down the 2, lower the power by 1, multiply the derivative of the inside, but the derivative of the inside is just 1. So if we pull off the power move on the next term, we'll pull down the 2, put it in front of the second coefficient, lower the power by 1. And if we take the derivative of the next term, we would do the same thing. Bring the power down, lower it by 1. So 3c3 x minus A squared. And then the next one would be 4c4 x minus A to the 4th. and so on. And by taking the derivative, notice that now what we have in the series is a single term up front without a parentheses, followed by a bunch of them that do. So if we put in a again, everything will disappear except the first term, and we can solve for it, which will actually be pretty easy. If we substitute the center a into the first derivative, everything disappears except the first coefficient, which means now we have a formula for the first coefficient. Let's write it up here. Our first coefficient is the first derivative evaluated at the center. And you might be thinking, okay, I see what's going on. We'll just take the derivative again. We'll get the next coefficient, and all of our coefficients will just be equal to the derivatives evaluated at the center. Well, not quite, because let's see what happens if we do this again. I'll get it set up on the next page. Okay, so there's our derivative, and remember, we've already got the values for C0 and C1. So what are we going to do? We're going to take the derivative again. But this time when we take the derivative, we're not just going to get C2 up front. The derivative of the first term is 0, so that's gone. For the derivative of the second term, we would leave the coefficient alone, then take the derivative of x minus a, but that's just 1. And so we end up getting 2C2 when we take the derivative of that guy. Plus, when we take the derivative of the next one, excuse me, didn't mean to erase that. When we take the derivative of the next one, hello, draw, thank you. We would use the power rule again, bring down the 2. So we'll get 3 times 2, which I know is 6, but for reasons which will become evident in a little bit, I'm going to leave it as 3 times 2. Plus 3 times 2, C3, x minus a, lower the power by 1. And when we go to the next term, and you'll notice I'm catching up with the terms that I have written down, but remember, both of these go forever, so plus dot, dot, dot. The next term, this one right here, if we took its derivative, we would bring down the 3, but there's already a 4 out there, so let's write 4 times 3. C4, lower the power by 1, and then the rest. And let's see what happens when we evaluate the second derivative at the center. Well, we get the 2C1. I'm not sure what this guy is right here. Well, we've got the 2C2, excuse me, plus, well, everything else would zero out, because when you put A here, this is equal to 0, that term's gone. This is equal to 0, they're all gone except for the 2C2 up front. So we really don't have to do a lot of figuring, because we already know that putting the center into the second derivative will equal 2C2. So if we want to solve for C2, we just have to divide both sides by 2. And therefore, we get that C2 is equal to the second derivative evaluated at the center over 2. And we could repeat this game over and over and over again, but I wanted to get to this one because it's the first one where we actually have more than just the derivative. If you were to repeat this by figuring out the third derivative and evaluating it at a, I'm going to leave it as an exercise for you to physically do it, but here's a summary of what would happen. This guy would disappear when we take its derivative. The derivative of the next term would be that times 1, so we would get that. The derivative of the next term we would bring down times 2, this would get lowered to 1, and then we would have all the stuff at the end. So what would be left when we put in a? Well, everything starting here would disappear when x is equal to a. The only thing that wouldn't is this guy, and so we would get 3 times 2 times C3. And I know that's equal to 6, but there's a reason that I'm not writing it. That's 6. So C3 is equal to third derivative, evaluated at the center, over 3 times 2 times 1. Oh, wait a minute. I don't need that times 1. But it doesn't change anything, doesn't change the value. But why do you think I wrote it? Does this guy look familiar? That's a factorial, and specifically it's 3 factorial. And if you go backwards, 2 is 2 factorial. And this guy is over 1, but that's 1 factorial. This guy is over 1, which is also equal to 0 factorial. So I'm going to go back and retrofit all of the coefficients that we calculated to be over a certain factorial. And it's not an accidental factorial. It's the factorial that matches the subscript. 0, 0 factorial. 1, 1 factorial. Same thing with the rest of them. 2, 2 factorial. 3, 3 factorial. So we can quickly make a generalization. Now, this is kind of loosey-goosey math. We're just figuring something out. This isn't a rock-solid proof, but I'm telling you right now that it's valid. In general, we can figure out that the nth term, so we'll say Cn, is equal to the nth derivative. And the way we're going to write the nth derivative is like this. Evaluated at the center over n factorial. That's kind of important. We're going to highlight that. Oops. Hold on, folks. Screen's going everywhere. All right, let's highlight that. There we go. All right, but we got what we came for. We got a formula that calculates the coefficient when we do a power series expansion centered at A, which is right here. So we can replace, and oh my gosh, I can't believe I did this. I wonder if any of you caught that. And the thing I just highlighted, there's a subtle error in the summation. There's a subtle error here. See if you can spot it. You see it? The subtle error is the subscript for the C should not be 1. The subscript for the C should be N. Again, minor detail, no harm was done. I don't believe we made any other errors. Of course, I could be wrong. Come on, draw the N. Thank you. But we now have not only, we now have the representation of the function's power series. We don't know the interval of convergence yet, but there is one, or presumably, because we found a formula for that coefficient. So what does this mean? This means that our function is equal to the following sum. N equals 0 to infinity. We now have the formula for the coefficient, which is the nth derivative, evaluated at A, over n factorial. And remember, that was the coefficient of x minus a to the nth power. We'll discuss convergence and interval of convergence and all that, but congratulations. We just invented something that is incredibly useful in applied mathematics, because what this thing does, under the assumption that the function is infinitely differentiable, it represents any function you want as an infinitely long polynomial that converges on some interval centered at, in this case, centered at x equals a. So why is that important? Because polynomials are easy to do math with. They're easy to differentiate and integrate. They're easy to evaluate, especially from a computer perspective, whereas other functions, not so much. All right, so we're going to summarize what this thing means in the next video. I already know this one's gone on quite a while.